开始上课了。So last week we introduced how to define the particle in the representation of anchors. In particular, we emphasize that this has to be the unitary representation of anchors. And Wegener previously showed, proved all these unitary irreducible representations are classified by these two numbers. Notice that M, we also know the physical meaning of M, which is mass, the gas mass of the particle, and the speed, J. This is very convenient because then we can easily justify something. Whenever people say someone told you they found some particle, and you can immediately compare it to mathematical result. Fundamentally. We also talked about how to embed particles into fields. This is also important. In a sense, this is only come from the representation theory. But this procedure tells you how to look into the field, find the particles, how to embed particles into fields. In particular, this shows some very physical content of field theory, even in the classic level, right? Previously, my dynamics is okay. This course is about field theories. So just write down some field theory. Field theory could be categorized into scalar or vector or tensor or whatever. A spinor, right? That might be your first impression. But this, of course, tells you that that's not enough. Okay? Suppose someone someday told you that, okay, I found a new field. The field looks like how many range tensor. If that's the only information, you immediately justify. It's not enough. Say found some new physical new field theory which corresponds to some. From procedure, we explicitly see that even for some kind of same type of field, which is a mu, which is one vector field, then you can actually construct a different Lagrange has different physical content, even different amount of liquid field, which means you want to interpret these particles completely different concepts. But geometrically, they might look similar, but they can both be described as tensor field. Okay. So this is also important. So we introduced the spin field, one field. In one case, we introduce both masses. Okay. And this provides an example just like I just said. Okay. So in order to extract the full content of some field theory, even in the classical level, you have to really specify the dynamics of Lagrange. Only after that can completely describe. So last part, last lecture, we introduced also very important concept, which is gauge markers or gauge centers. Okay. The name by itself is a little bit confusing. See, sometimes you might hear the people claim that gauge symmetry is not a symmetry. So what does it mean? So indeed, so you can put it here. If you only think the symmetry to faithfully reflect the relation between different physical states, in that sense, gauge symmetry is not a symmetry. So to see gauge symmetry is not a symmetry, we really mean that we have a very high standard to name a symmetry, namely only global symmetry. In a sense, it does not faithfully relate, transform physical state, but not send one physical state to another. So in order to get avoid of this redundancy, of this gauge redundancy, we have to go with the gauge so-called gauge fitting procedure. This will essentially allow you to pick up the real physical degrees of freedom. See, we studied one example, which is Maxwell theory. By choosing Coulomb gauge, we explicitly see there's only two polarization directions, or two degrees of freedom. So we will continue to talk about how to understand the gauge field with the gauge theory, namely the Maxwell. So one immediate thing you can try is just add matter. Right? So last week we only talked about photon, Maxwell theory, charge. We simply just add matter. So what do we mean by this one? So in a few weeks ago, we already see how to construct a theory for complex scalar. Okay? If you remember, there we already showed that there is a global transformation, a global symmetry associated with phase rotation of a complex scalar. With this complex value, you can rotate by phase. You can see actions invariant. Now, what you need to do is slightly generalize that transformation. Then consider a complex scalar. Again, so now you just perform some transformation to see not only a global phase without x-dependent, but you can actually promote it to a x-dependent phase rotation. Okay. Now, if you insist that the previous free field Lagrange, you immediately find that that's no more invariant. If you promote the phase to a function of x-dependence, okay. Say, if you only think about such term, mass term, say, for instance, this is still okay. Under this rotation, this is invariant. Okay? But the derivative term is not. Okay? See, if you consider this term, this is not okay. It's not invariant under the such kind of transformation. So what to do is, in order to overcome this, okay, we have to introduce another field. But this is nothing but the gauge field, okay, or the electric field we studied last week. Okay. Now let's go through this procedure step by step. First, in order to construct some Lagrangian invariant even under such transformation, we introduce another field. Okay, see, I just add another field into the system to in the same time I demand the other field also transform. Okay, for instance, transform in this way. The alpha is that same alpha x. Okay. Then you can check something. If you check something, for instance, you can check such kind of improved or modified derivative. Sometimes we call this is covariant derivative, and below this is capital D U. So you can check this one, how this transform under this closed transformation for the two fields. Okay, just plug in. We need to realize it's nothing. It's A or A transform. Okay, so you just add up another term. Okay. Now phi of course also transform. So we have transform phi. Okay, so transform phi. Then the derivative, because phi itself transforms the derivative action on phi. So here the derivative should be understood action is transform field, including this alpha. Then you immediately realize that this term was cancelled. Okay, so this is nothing but e minus I x. And by definition, this is nothing but. So you realize that such kind of combination or covariant derivative act on phi is actually transformed covariant. Okay, not invariant, but it transformed in a nice way. Okay, see, nice way means it's only up to overall phase factor. This essentially means that I can take advantage of this fact and construct something which is invariant. And I also want to include the dynamics of the A mu field itself. And take it the dynamics as essentially the Maxwell theory. Then I put everything together. You can easily check such kind of construction is indeed invariant. Is invariant under the transformation for both phi and A mu. Okay, we call those transformations gauge transformations. So this is essentially a gauge invariant. So by this approach, we can couple the photon to other charged matter. So in this case, charged scalar. Okay. By demanding the gauge invariance. Okay. By demanding the gauge invariance. It's better to be gauge invariance, right? The gauge transformation. The theory has to better to be gauge invariance. Okay, if you have something with non-invariant by itself, the construction is not good. Okay? But because gauge invariance only show the redundancy. Okay? Redundancy. So this is called the scalar QED because we couple the scalar to the photon. So this is called the scalar QED. And you can play with all the game we learned before for this new theory. Okay, you can analyze, for instance, probabilities, Feynman diagrams, right? After you carefully quantize this theory. So, yeah, so scalar QED by itself is an independent chapter you can write in a textbook. Into a textbook. So it includes a lot of rich physics. So now let's try to figure out something maybe important. It's again it's related to this gauge symmetry. It goes back to this one. Okay. So this is a good example. So let's classify something. First, in this case, what is how to distinguish the so-called global symmetry and the gauge symmetry? Okay, that's the first question you want to ask, because that's confused a lot of the students, okay, early researchers. Sometimes they're just bothered by the different names. Is that they're better names? With this gauge symmetry, better name. Since not everybody knows this, how to distinguish the details, named wrong or mislead, one can easily be confused by what is the relation between global symmetry and gauge symmetry, even though we know gauge symmetry is not a gauge symmetry, it's not a symmetry. But there are some relations, right? You cannot say that's completely unrelated. That's also not true. Okay. So what are the relations between these two? The first relation is you can realize that the gauge symmetry parameterized by some function, function x. Okay. So sometimes we call such kind of symmetry also local symmetry. It's also not a very good name. Because this is principle. This is a local function. It's a local function. Sometimes people use this. So if you have such a parameterization, of course, you can immediately see, okay, this is just if I did nothing but just set this function to be a constant, okay, alpha as a constant. Then I immediately find a good global symmetry, right? Because it's nothing but I just set a function. Okay? Is that clear? Then this is the global symmetry. Now, if you do this, then immediately I employ this Röder's theorem. You can get a lot of interesting stuff. Right? The current, you check the conservation of the current, such kind of thing. You can also talk about a lot of physical properties of the current. Okay? Yeah, that's all good because we know this is a very physical consequence from this global symmetry. But it doesn't mean gauge symmetry includes the global symmetry. Okay? Okay? Don't think in that way. These two things, even there is some kind of relation, but these are rather independent. Okay? It's not completely unrelated, but they are independent. Okay? But don't think something like okay, one belongs to the other. No, that's not true. Okay? Okay? It's not like a subset and a subset. Global symmetry is not a subset. They're just different things. So we continue to distinguish one is local, another is global. Okay? We don't think local is global either. We also don't think global belongs to local. It's distinguished. That's reasonable, right? But the physics constants are completely different. One captures the redundance, the other captures the incontrollable. Okay? Yeah, so instead, if you doing this, doing this, and we can further do the other procedure. Yeah, you can actually work out the corresponding there's current for scalar QED. You can even prove. Okay. Now we move to the other also important question, which is how to quantize. How to quantize theory. Okay. So far, we only, to be honest, we only made it very clear we know how to quantize a free scalar. Okay. And by perturbation, we know to some extent how to compute the correlation functions for interacting theory. Yeah, that's what we know. And we don't know much. Now, let's look at some details about this new theory. We mentioned some time ago, there are different ways to represent the complex scalar. Okay, complex scalar. One way you can just represent it by a phi star, is what I just okay, okay, right. The other way you can represent the complex scalar with a split or decompose to two real scalars. Okay. Right? Now, if I take this viewpoint, meaning that the complex scalar is nothing but a pair of real scalars. Okay? Okay? Just be careful how to pair them. That's it. The physical content, what I'm trying to say, physical content is really equivalent to real scalars. Okay? Right? Because this is the identification. So this means what? This means that you can just follow the previous quantization to just quantize the phi 1 and phi 2. That will be equivalent to quantize the complex. That clear? That should be okay, right? So I can even organize this yeah, I can organize these two fields. It doesn't matter how to write, how to understood that the content is really scale. Doesn't matter which way. I can write it in this way. Okay? I can write it in this way. Okay? I can view this just a two-component object. Okay? Two-component object. It's a little bit confusing. This vector does no meaning for some orange vector in coding space. It's not. I just wrote it. It's defined. Yeah, we already said we know how to quantize phi 1 and phi 2. Now this just means I also can immediately write down how to quantize this two objects. Okay? So put them together. Okay? Without doing much. Just package them together. So for instance, you can write this way. Right? This is what we learned in the first lecture, first two lectures. Okay? You see, for each phi 1 and phi 2, this is what we already know. Okay? How to quantize in this formula. means how to define the field and truly operate with AA diagram. Okay. Right. Now, by knowing this commutation relations of this AA diagram, I essentially know how to operate the meaning. That can be used as you know how to quantize the field. Now you already write down the field in terms of clear operators. As I said, there are two components that just packaged together without doing anything. You just read it, right? Read it line by line. It's just completely equivalent to the free real scalar quantization. Okay. Is that clear? Now I can also improve the notation a little bit. I can improve the notation a little bit. I can just revise the right-hand side this way. Meaning that I using some kind of index notation. Okay? I use some kind of index notation, but really without doing anything. I can rewrite it in this way. Right? I just use the index notation to represent this. Okay? Where the epsilon j index run from 1 to 2, and epsilon 1 is 1, 0, and epsilon 2 is 0. Okay? Yeah, it's really just rewrite, right, without doing anything. Rewrite using this funny index notation. So why I want to pay a few minutes to rewrite this looks trivial or expression. This you can get some feeling about once you have some field with more than with more degrees of freedom, meaning more than 1 degree of freedom. Okay, you can just try to express it this way. Okay, if you know each single degree of freedom, how to quantize it, then essentially you package it. Okay. We can try to package it. Yeah, that's why I want to show this for you. But the important thing is this epsilon something similar to the polarization vector. Okay, so this vector itself really only does the job to project down to the component. Okay, it just tells you which component you are now doing quantization. That's it, without anything new. Okay, anything more than that is only a job the epsilon vector does is this one. Okay, it really takes a single duty to tell you which component or which degrees of freedom you are now quantizing. Okay. Now, by knowing this, we can immediately write down the quantization formula for the Maxwell field. Okay. So what about for the Maxwell, the mu? Okay. So we immediately write down similar formula for mu, because we know how to represent the Fourier space. The mu field. Okay? In particular, we already know the only physical degree of freedom. Was represented again also by some polarization. Okay? That's only the physical degree of freedom. So you now just combine with the polarization vector, you can write down the quantization. Essentially, we already finished the complex scalar. The only remaining field is the Maxwell field. But the point is, this we can learn the experiment from this complex scalar quantization. We immediately write down the quantization for the new. Okay? So what is that? We just follow the size and follow the same pattern. So write down carefully unify formula. Right. I also this time I also has some index run from 1 to 2 because there are only two physical integers. Okay, I use the R index. Now we also know already last time there is a polarization vector. Okay, goes like an epsilon mu I. The difference compared with this complex scalar is a new index. Okay, the new index. Okay. Because this is not a trivial pair of two scalars. It's a vector. It's really a vector. Okay? When you rotate the vector, when you rotate the vector, okay, the component will mix, okay? But that's the difference between vector and scalar. So this polarization vector, which means the polarization vector has to depend on. It's also a vector. The transverse polarization vector. Now, the remaining same structure will be the same. Okay, essentially the same. It's A operator. It's P I index. P means for given for a fixed for a given P momentum, right? Right. We learned from the first few weeks. The quantization essentially tells us for each P there is a harmonic oscillator. It's also the same. And I is supposed to respect to this I, right? This I just tells which degrees of freedom we are now assigned this harmonic oscillator. Okay? If there are more than one, I run from 1 to 2. And instead, what other structures do the same? And there's a conjugate part. Let's write it as in this way. That's it. Okay. I put a star here. Why? We showed the last time you can choose some base. There are two independent base vectors. Polarization vector or general polarization vector, right? You can choose whatever base you want. Some guy may just try to want to choose the base. Say, for instance, there are 4 components. Someone might choose a base with some components with I or minus I or something. It could be a complex one. Okay. Last time we choose some real one. The real one, then you take a complex conjugate, not necessarily to put the complex. But suppose you do have some favorable base, and there's a conjugate. So, like the complex scalar, these two polarization vectors really. Two polarization really only take duty to tell which degrees freedom you are now quantized or equivalent to project out. On physical degrees freedom. Much more than that, okay? It's just some like funny projectors. Okay? It's not an operator. Not an operator at all. The only operator here is formula A and dagger. Okay? So you should try to extend the your a dagger formula for free real together a little bit more general. You can understand. The only, I would say, the only a little complicated thing here, the peak dependence, but that's also understood. Because for photons, depending on which the propagating direction, okay? So the photon, such kind of momentum, the polarization vector, momentum, that's one reason. But the point is, for all the, by choosing some particular base for all the given p, okay? So we're not going to, there is, of course, again, there is a rich story behind. See, this is the final answer, basically. I just show you the answer. This answer is so natural, and we can easily understand the physical content or the meaning of this formula. So we just escape all the intermediate procedure. Namely, in history, people try to go step by step how to quantize a Maxwell field. Okay, that's a tedious experimental calculation. For instance, you can first try the, because in the beginning people don't quite understand what's the relation between gauge fixing and quantization, for instance. Then if you don't know that, okay, then your first try will be let's just quantize, just stupidly follow the scalar case. Okay. Say, for instance, I can quantize a 4-component or 3-component object. Okay. Then you're doing by setting this commutation relations or quantization conditions, you actually face some trouble. Okay. For instance, if you do, okay, hopefully you still remember some content that we introduced last week. In last week, the first step we just dropped the 0 component of this a new field. Remember that? Now, still you have 3, right? In principle, you still have 3, right? Now, you can try, for instance, you can first try, let's just quantize this 3 degrees free. Okay? Try to employ this commutation relation or quantization conditions. For instance, I can try to read off the conjugate variable for some AI, okay? And then put a commutation relation there and try to work out the quantization, right? That's the standard procedure, right? But then you immediately realize that if you don't use this gauge fixing condition, you have trouble. Okay? Some of the quantization or commutation relations will be contradict with the gauge fixing condition. Okay? Which essentially means it's not a good quantization condition. Okay? Then in order to respect the gauge fixing, it's better to first really employ as much as you can. Take use of this gauge fixing condition. Really project out all the unphysical things. Okay. Eventually, and then just target to this physical degrees of freedom and then quantize. Then you know it's okay. Okay. Then you arrive at such kind of formula. But the formula itself is simple. Right? Okay. In order to get there, it's not trivial. Okay. In order to arrive there, it's not trivial. But this is this can be easily understood. So we choose to just escape this. We don't have much time. Okay. But some of you may not be satisfied, right? By only knowing this one. And this is good, but it's not enough. For instance, what about for instance, if I want to compute some Feynman diagram related to this associated with photon, then it's better to know the photon property. So the next question you might ask, this doesn't tell you what is the photon property. So what is the photon property? What is the photon property? This is the next question. In principle, you can, of course, make use of this one to compute the Druckmann functions, right? To follow the procedure we introduced for scalars, okay? Do step by step, okay? And then eventually you came up with the time order Druckmann function, okay? To get a result, both in the coordinate space and in the unit space. Okay? then you obtain this photon property. That of course was okay. But now we want to try to immediately get a result. We choose a different approach rather than this canonical quantization, rather than this Coulomb gauge. By the way, this is only true under Coulomb gauge. Okay. Okay, as we emphasize, because there's a gauge redundancy. Even though gauge fixing is not unique, but you have to specify. Okay? To work out the physical content, you have to first specify which gauge fixing. So this is under Coulomb gauge. So in order to introduce or immediately work out the photon property, we choose another gauge, which is called Lorentz gauge. So let's compare. You might say, okay, are these different gauge fixing completely arbitrary? And but it's not. It's not, right? So let's try to understand the difference in the different gauge. So Coulomb gauge, there are advantages and disadvantages. The advantage is, of course, as said, you can really immediately realize the true physical degree of freedom where it is. Okay, that's the advantage of Coulomb gauge. But what is the disadvantage? Can you see what is the disadvantage? The disadvantage is there's no Lorentz invariance, you see, or covariance. Because you start from some A mu field, you project out some degrees of freedom. Okay, you essentially break the covariance. Okay. That's the disadvantage of the Coulomb gauge. So you might think for other purpose, maybe some other gauge might be convenient, for example, Lorentz gauge. So what is Lorentz gauge? Lorentz gauge is defined. It's just previously remember that Coulomb gauge is going like that way, right? It's going like that way, right? This is a Coulomb gauge. Now we choose another gauge, which is really set by a pair of contracted new index. That's why we call this Lorentz gauge, because it preserves Lorentz invariance. Because gauge condition itself is Lorentz invariant, you see? It's contracted over a new index. Okay. This is called the Lorentz gauge. To work out the photon propagator, it's better to stay in the Lorentz gauge or switch to another gauge. What do I mean by that? There is a practical reason for that, which is if you don't do that, if you don't choose some. Okay, let me explain step by step. So how to work out propagators? As said, we want to escape this canonical procedure under Coulomb gauge. So what is the way? The way is we can try to choose some convenient way. So remember that in the scalar case, we essentially in the momentum space, if you want to write down the propagator, you can simply put an I epsilon to realize all this physical time ordered property requirement for the two-point functions, right? Remember that? We justified this by the contour integral, very careful. Now, in this case, I just want to be quick. Then I can first try to write down the propagator without I epsilon and just put the I epsilon by hand. Okay? But I don't want to go back step by step, justify once again. Okay? So I think the I epsilon prescription is still okay for the purpose to construct a time-ordered propagator for the A field. Okay? I just write down. So job is going to compute such kind of object. Okay. And as said, I don't want to go step by step. I just want to find the propagator result I epsilon and then put the I epsilon by hand. Okay, I just want to take this approach. Now, what is the propagator result I epsilon? Previous for free real scalar, if you still remember, for massless case, for instance, that's simply 1 over p squared. Remember that? Remember that? That's the propagator in momentum space, right? Now we put I epsilon plus I epsilon. Then we get the correct propagator for, in momentum space. That's what we did for scalar. Now in this case, we also want to choose this approach. Now the point is, we can even in the free scalar case, we already we can understand that this comes from you just take inverse. You just take inverse for the box operator in momentum space. Okay, because p squared is essentially the box operator in momentum space, right? Remember that? Because box is partial mu. In momentum space, it's just a p mu. P mu is p squared. Is that clear? So there's an even more simple way to just read off the momentum space propagators. You just take the operator, play the same role as the box, okay? For the field, now for the new field A mu. Then you take the inverse of that in momentum space. That's the answer. Then you put some I epsilon in the denominator. That's it. That's the procedure. Now, the point is, if you're naively doing that, following the equation motion for A mu as what we introduced last time, it's very difficult. You have trouble because that operator is not has no inversion. Okay, that operator has no inversion. What I mean by no inversion, I think about the matrix. There's no inversion. The determinant is 0. And the way to get around that one is essentially combined with this particular gauge choice, the Lorentz gauge. So the Lorentz gauge. Now we try to work in the Lorentz gauge to find the propagator because it's a Lorentz covariant or invariant. Now the gauge condition, gauge fixed condition, or the constraint gauge fixing. This gauge fixing Lorentz gauge. The Lorentz gauge condition can be achieved or it can be realized by change the Lagrangian. Previously, when we talked about the Coulomb gauge, we always keep in mind that we have to set the gauge fixing condition or the constraint condition additionally, right? By some kind of God-given condition. You always keep in mind there is a constraint condition there. Okay, combined with everything else. Okay, always combined together. You cannot forget that. Now, some students might just came up and say, why don't you just improve your theory, automatically realize the gauge condition, gauge fixing condition? That seems very good, right? You don't need to always remember it. Okay. It's already here. It's out of the theory. That's also a choice, right? So to deal with this Lorentz gauge, precisely there is a beautiful way to realize this idea. Okay, I'm not just trying to change the original Maxwell's Lagrangian to automatically realize the Lorentz gauge condition. For instance, I can just change a little bit the f squared Lagrangian, just put by hand a new term. Okay. Now, how is this possible? How is it possible to how this theory immediately realized this condition? How? You see it? There's one way to realize that. If you view the Kc, this coefficient, Kc, if you view a Kc is an independent field, okay? Now here Kc is a constant, but you can also view Kc can change, okay? Okay? Kc can change. Kc has to satisfy the variation principle. Then that's equivalent to set this condition. See? Remember that? If you Kc has to respect the variation principle, you have to derivative L derivative Kc, right? Right? That's essentially this condition. Right? That's why we see this improve the theory can automatically include that gauge fixed condition. Okay. So this time sometimes this Kc is sometimes called as a family name, the Lagrangian family, Lagrangian multiplier. So what's the point? Why we want to do this? Because once you improve, you change it a little bit in this way, then the difficulty to work out the photon propagator, that difficulty disappears. Okay, you can do it. Really, just work out the propagator under this new improved Lagrange. Okay, right? What is that? So for the change the Lagrangian, as said, you can take the box for a mu, okay, some kind of box for a mu, or the operator act on a mu, you get the equation motion. That kind of operator you can take inverse. Okay, for instance, with delta Kc, you can work out the equation motion for the A field. The new equation motion will be the box A mu plus the term depends on the C. Then partial mu A mu equals to 0. Okay. Now I get this one. The good thing is this new operator is we can get an inversion. We can get an inversion to obtain the property. Work it out. And after doing the inversion of this, we can obtain the property. Say in let me write it in a standard way. In the coordinate space, we can write as a p interval, and the integrand will be the momentum space propagator with this I epsilon as said. There's a non-trivial numerator, which is g mu nu plus the p minus 1 p mu over p squared. And the remaining part will be the same as the all other field scalar case. This is just a Fourier expansion. You can think of this is just a Fourier expansion of the photon time order property. Time order 2.5. Now, from this result, we need to realize that this is nothing but what we want. Okay. So this part has to appear in the Feynman rules. For instance, if you want to following, giving you some Feynman diagram, include some photon property. Okay? This part is important to write down. Okay. A few remarks. As you see, we didn't specify the value of the Kc. right? We didn't specify the value of the Cassie at this moment up to now. We just think Cassie may take a different value. We just keep the Cassie dependence there. Okay? We just keep the Cassie dependence there. Now, when you read the textbooks, different textbooks may also refer different values of the Cassie at different gauge. Okay? And as a total, some result with this Cassie dependence, you might call it if this is some kind of covariant gauge. Okay? So this is very weird names, right? This is called Lorentz gauge. The previous one is Coulomb gauge. Now this new improved, this method to realize the Coulomb gauge, but with a Cassie dependence. Sometimes people call it covariant gauge. Yeah. But the point is, you have to understand the name is it's not a big deal. Right? You have to understand the meaning of this formula. Right. Yeah, this is one way to work out the photon propagators. Of course, there's different interpretations. There are different approaches to arrive at this result. Yeah, we can try to learn yourself. Yeah, for instance, you can take the Cassie equals to 1. Okay? That's a typical choice. Now, how to understand the Cassie equals to 1? Cassie equals to 1, this new improved term is not trivial, right? It's still there. It's just a half partial A bracket square. Now, how to understand that one? Why do we want to put a fancy new term into there? The point is, if you look at the equation of motion, by imposing this gauge condition, okay? As I said, this gauge condition is a very priori condition, okay? It's like a God-given condition. You have to always set this condition, okay? No matter in classical level. Now, if you look at the equation of motion for a mu, which we studied in great detail last time, right? Now, by using this new gauge fixing condition, you will get a new phase of equation of motion, right? Because this gauge condition will certainly simplify the equation of motion, right? That same equation of motion can be realized precisely by just taking this new Lagrange. That's the point. Okay. Okay. This is why we can claim that improved Lagrange can realize the gauge condition. Okay. Now you can be more that's the level of equation motion, right? What I just said is the equation motion. Because if you only care about you arrive at the same equation motion, then you can take the Cassie to 1. That's enough. Okay. Now I can even take the Cassie to be arbitrary. Okay. Then this is slightly different, but even more stronger condition. That means even at the Lagrange level, you already automatically include this condition. Okay? It's not only the equation motion. Okay. You see, because this is the Lagrange multiplier. Okay? Later, at this moment, you can understand that the Lagrange multiplier itself has to respect the vibration principle. That's equivalent to set. Later, when we learn the path integral, you can make it more clear. It's just this variable integral. It's equivalent to set. Okay. This is a priori condition. Okay, anyway, there is a rich story there. You can try to understand all the details carefully. But the point is, we do have one way to work out precisely the photon propagator, even though there is a funny Cassie dependence there. This is prepared. This result is prepared to work out all the Feynman rule result, the Feynman diagram result. Okay. So this is the end of the discussion about the spin one field and the gauge invariance. So next, we want to continue to discuss. By the way, I didn't derive it because you should derive it from equation motion. There's a homework. Next thing, we want to continue to a field with even different speed, even other integer, which we call the Spinors. That's the main topic of today's lecture. So the main topic of today's lecture will be my favorite topic. Let's try to introduce this seriously. So what is the Spinors? So in order to understand what is the Spinors, we go back to the Lorentz group. Okay. By the way, even last week, I hope some of you may ask a question. We just show the result of Wigler's proof, right? The mathematical theorem. See, all the unitary reduced representations of Poincare group is classified by two integers. We all know how to define the mass, okay? Yeah, that's you should know in your special relativity course, right? This is the rest mass. This is the Lorentz invariant object, for sure. But we didn't really define what is spin, okay? Right? So the question might be, what is the spin for some of you, right? So you told me there's a good quantum number, the physical meaning is spin, but you didn't tell me what is spin. You didn't even define what is spin. So let's take this job now to really see how to define this one. Why this is related to the Lorentz group, okay? Right? So also some of you asked last week how to understand the different representation. Right? So what this question motivate us to go back a little bit back to the Lorentz group. So first of all, in case some of you even don't know Lorentz group. By a group, we usually mean some element, okay? A set of elements, they follow some rules. So they just we should write the element by certain GI. This is the group. And we know how to also give a group. Essentially means we know how to multiply the different elements, right? Which kind of rules? And there has to be, the identity or inverse for the element, such kind of constraints or restrictions for this set of elements. But then, given this, what is the representation? We are physicists. So we really care more about the representation in some sense, okay? Rather than the abstract structure of the group itself, okay? And that looks a bit mathematical. But we're physicists, we're staying in the real world, okay? And we're interested in this group theory just because the real world is often under this group structure. And in other words, there are many physical objects that stay in the representation. So what is the representation? A representation is a particular embedding of this group element, let's say GI, into operators that act on, say, a vector space. Okay. So imagine you have some vector space. So for physicists, the typical vector space will be the Hilbert space, right? Suppose you have some vector space. Now you can associate or you can embed this group element into some operators, which essentially means because the operator does the job to transform the vectors, right? Right? You can think about it just the matrix, okay? The matrix transform the vectors, okay? The operator transform the vectors. This kind of transformation just follows a group rules, okay? Group elements. Just one-to-one corresponding to this group element. This is what we mean by a group, a particular embedding of this GI into operators and vector space. So if you realize, if you have such kind of realization, congratulations, you get a representation. How do we mean that representation, right? This is what we mean by representation. Representation means you really realize your abstract group element explicitly in some vector space, okay? I associate that group element, each group element with a certain operator. That operator does the job to transform the vectors, okay? Now, as we also mentioned last time, sometimes we a little bit sloopy. Sometimes we also, let's put a correct remark here. Very often, we also talk about the vectors. The vectors on which the matrix, the operator, the matrix act. We also talk about such kind of vectors as being representation. For instance, particle state, okay? We introduced last time. Particle state is essentially such kind of object, such kind of vectors, okay? Okay? But mathematically, it's really the operator or the matrix that represents the group element, okay? But sometimes we want to emphasize which are the physical objects. Sometimes we also just call the particular vector state. They are transformed, those objects which are transformed. We also call them as being the representation. Okay? But to be precise, or mathematically, or technically, we should know that it's really the matrix or the operator, right? Or the embedding, particularly embedding for GI into some operators. This is the representation. Okay. This is just re-understand what we learned in the first course, because we already introduced the Lorentz transformation. It includes the rotations and the boost. Okay. In particular, we write explicitly this as a matrix which transforms the Lorentz vectors. Okay. We just go back a little bit. Now let's review what we learned in the first lecture, which is about Lorentz. In the first lecture, we defined the Lorentz transformation, right? The lambda the matrix. Okay, so we have defined property lambda transpose G lambda equals to G. Okay, remember that from the matrix. This is our definition for the Lorentz transformation, and this will include the rotations in terms of 4x4 matrix. Yeah, these are the three rotations. Prime rotation. Sine, minus sine. These three 4x4 matrix take the job to rotate the vectors, and they also boost, right? There are three additional boost, which is associated with boost parameter, which is beta. So we use theta. We use theta to parameterize the rotation, and we use beta to parameterize the boost. Okay. This is essentially the review of what we already learned. Okay. So the cosh, beta, sinh. This is sinh. This is beta z. This is the beta. This is the beta y. And this is the beta x. So these are the 6 matrix, and we should emphasize all this theta, both theta x, theta x, theta y, theta z, all these betas, they are all finite parameters. Okay, not a small parameter, but finite parameters. And these metrics are essentially the representation, right? If you take the definition of that, that's the representation. This is essentially the representation for a Lorentz group. Okay, a Lorentz group. They act on this 4-dimensional vector space. Okay, they act on the 4-dimensional vector space. Now, let me ask you a question: are these representations unitary or not? We also learned what is unitary last time. Okay, are they unitary? Can you tell me? Yes. Of course not, right? We know what is unitary. Unitary means the matrix has to be satisfied, like U diagram to 1. Okay, these are certainly not. Okay, certainly not. If you, for instance, if you think this theta, beta are real parameters, they are certainly not unitary. Okay, they are not. Because you can check it. You take a U diagram, you don't get 1. Okay. Okay. So unitary structure always associated with some phase, right? If you have something like exponential to the I theta, that's good. Okay. These are not. So this somehow explained why last time we by introduced Wigler's result, the unitary is very important. Essentially, following a group theory, we already understood there's no finite dimensional representation to give a unitary representation of Poincare. The only possibility you have to go to infinite dimension. That's why we have to get to the field theory, okay? Rather than to just try to guess something like this to give a representation for the Poincare group, okay? But because the theorem, some theorem just, the mathematical theorem says it's impossible, okay? So yeah. So the key message now you have to know is that it's completely non-trivial to realize a unitary representation of either Lorentz group or Poincare group. Okay, it's not trivial. It's very non-trivial. Okay, because you can check all your familiar finite dimensional representation metrics. They are not unitary. Okay, you just check by correct whatever textbook. Now we want to ask another question. So to understand this Lorentz group better, so see, let's go in this way. So here we define what is the representation. Then for sure, given a group, the same group, you can have different representation, right? Then the immediate question you can ask is, then what do we do? If someone has this representation, the other one has another representation. They are completely different representations, but the group is the same group. So how to extract the intrinsic property of the group, which is independent of a particular representation? That's the question, okay? Okay? That's the question, right? So we want to extract some property which is more intrinsic rather than dependent on particular representation. So how to do that? There is a way to do that. So to extract the intrinsic property also say the Lorentz group, we can try to check that. We can try to check it or extract the infinitesimal transformations. So both these rotations or boosts, we can write down an infinitesimal version. Okay, we should be familiar, right? Because when we talk about the global symmetry, we even take use of these infinitesimal transformations many times. Okay. So in the 4-vector, this is so-called 4x4 matrix. We call these the 4-vector representations. Okay, because the vector space is 4-dimensional. Okay, in the 4-vector representation, the infinitesimal transformation, we can get the infinitesimal transformations. Let's say delta x0 equals to y. Okay, now I write everything in the component without varying all the upper dimensions. So delta x okay, this is a trivial exercise, right? You just take a small parameter limit, okay, or you do Taylor expansion. You treat this theta or theta or this beta, they are very small, then you have an expansion, right? Right? Then you have an expansion. You have the leading term, okay? You just read off those infinitesimal transformations. You can get such relations. Because this is a matrix. This is a matrix. This matrix sends some 4 vector, which I denoted by x0 and xi. I run over from 1 to 3. Okay? So there's x0, x1, x2, x3. There is a 4 vector, which is x. They are transformed by those 4x4 matrices. Okay. Now you can read over. Now you already know the final transformations. It's trivial to work out the infinitesimal one. Okay, you just do the small parameter expansion. Now by doing that, you immediately get this one. Now I put a tilde. Tilde means this is a small parameter. Okay, you can immediately get this one. But there's again there are 6 numbers, right? The number of the parameters shouldn't change. Now here there is an epsilon IGK. This is a totally symmetric, totally anti-symmetric object, meaning that I take epsilon 1, 2, 3 equals to 1, and the value and the sign flips whenever you exchange any 2 index. So this defines this epsilon IGK, right? I have epsilon 1, 2, 3, 1. From wherever you change the whatever 2 indexes, you get -1. You change twice, you get that 1. So this defines all the elements in this function. Now this is the infinitesimal version of that transformation. Now I can package this a little bit. I can package this infinitesimal transformation a little bit. I will get a delta x mu equals to I sum I equals to 1 to 3. I have theta I tilde. I will have a j I, and this will have index mu plus beta I tilde. I will have a k I of index mu. I just rewrite this one again, package that 4 equations into a single formula. This will act on this x mu 4 vector. Okay? You can just organize it, right? You can just organize. You can just organize. Organize this one into this one. By that, I mean that, right, these are just the parameters. Okay? These are just the numbers of parameters. And this ji and ki, you should view this is a matrix. Okay? Now, x mu and x mu are the vectors. Okay? So you can express the infinitesimal transformation on a Lorentz vector, write it in that form. In terms of these J matrices and the K matrices, okay? And you can write down this JK explicitly because you now know everything. It's just an exercise. To express the same thing in equal form. Now you will get the J1, the J1 will be 0, 0, 0, 1. These are of course again 4x4 matrix. Right? J2 will be I. J3 will be I. 0, 1, 2. Okay. You also have K, 3K. I just define I just defined, you should view this as a new kind of new definition for J and K. I just defined the transformation matrix associated with the small theta parameter, the J matrix. I defined the transformation matrix associated to the beta, a small parameter, as K matrix. Okay. The point is, I know everything explicitly. This is transformation here. I can just write down all these J and K matrices. 0 comes 1, 2, 2. Okay, I can write down the J and the K matrices. Now, as said, this matrix contains the information to capture the infinitesimal Lorentz transformation. Okay, that's the point. In order to get the intrinsic property of that Lorentz transformation, or Lorentz group, that intrinsic property has to be included in this J or K matrix. Okay, because this takes the duty to do the infinitesimal transformations. Now, how to read off that? How to realize that? So we also call this J as name for this J or K object. We call them such kind of metrics are the generators. We call these are the generators. Generators of the Lorentz group, right? You see, intuitively, it's reasonable, right? Because it does the small infinitesimal transformation. It's really the generator. You can think about many small transformations eventually realize the finite transformation. Okay, so in a sense, it generates any finite transformation. Okay, so that's why we call this the generators. We can even see this very precisely because you give me a lambda. Say lambda is some 4x4 matrix. That's the finite transformation. I can always write the lambda in terms of exponential y theta I j I plus I theta I theta. Okay. Right. So from here, you can also understand why they are called generators. Right. See. If you do Taylor expansion, I view this theta and beta as small parameters. Okay, you will get that infinitesimal transformation. To the perception, just go step by step. Right. Now you can also view this. You can also view this as a final parameter. If these are the final parameters, there is a e to the such kind of matrix. So in mass, mathematically, this should be there is a potential. The exponent is a matrix. Okay, so following the how to define mathematically the exponent in the matrix, just following the rules to define this object. You can also see these JK are really the generators. They are the generators to give these final transformations. Now, we're not satisfied. We're not completely satisfied by such kind of understanding. We really want to extract the intrinsic, as said, intrinsic structure of this Lorentz transformation or Lorentz group. That information actually was encoded as the JK matrix, but how to get there. That information was encoded in the commutation relation of the J and K. Okay. So with the generators, so one can check there is a non-trivial commutation relations Because the matrix is there, you can easily check it. So, okay. There's a commutation relations. It basically says the J commute. The commutator, which is J equals to, you get to another JK, okay? With the coefficient of epsilon I JK, just define epsilon I JK, okay? It's a completely anti-symmetric object. Now, if you commute Ji and K, Ji and Kj, you get the epsilon with K, and you commute Kk, you get a J. Okay? Is this familiar to you? In particular, what is this? You should be familiar with this relation at least, right? What is this? This is the relation, commutation relation for generators to give this commutation, right? Right? To learn maybe more quantum mechanics, right? You have a rotation, you have an SO3 group, right? The SO3 group is precisely supported by this generator. Then you can write down the commutation relation. Okay. But K is a little bit different because K does the job to do the boost. Okay. Okay. So K mixed with J. Okay. K mixed with J. But J can commute to itself. It means that there is a kind of sub algebra, a subgroup. Okay, which is supported by the J. I can already read it from here. Okay. So, so we call it is such kind of commutation relation defines the so-called SO1 comma 3 Lie algebra. This is not a group theory course, okay? I'm just trying to give you in a physical way how to relatively easily understand the structure. You see, as I said, from the beginning we have some already known finite transformations. We have some particular representations. Okay, we can write down some particular already 4x4 matrix. Now we're not satisfied. We want to pick up or extract some intrinsic property. Now how to do that? We see, since the group is like continuous, okay, the intrinsic property has to be encoded even in the infinitesimal transformation. Okay, so we first write down the infinitesimal transformation. Then we take out the parameters, just extract the matrices. The matrices does the job to do the infinitesimal transformation, which is essentially the J and K matrices I wrote there. Okay. Now, as I said, the intrinsic properties have to be encoded in these JK matrices. But this is just the matrices mathematically. How to get the information you want? Now let's try the commutators. Okay. Now you can just try the commutators. Now indeed, you find that there is a non-trivial and also very nice commutation relations among these J and K. Okay. Okay. Then we think this kind of commutation relation really does the job to include the intrinsic properties, okay, intrinsic properties of this group or algebra, okay. Essentially, the algebra is the version of infinitesimal version of the group, okay. Basically recall this is just the relation defines this algebra. The algebra is just a set of relations between these generators. That's what we call an algebra. Okay. So in group theory, this bracket are called Lie bracket. Lie bracket you can understand in a very formal way, but here we see explicitly they are just by commutation relations. Just you can define this as AB minus BA. So as I said, this part already show the sub-algebra, the sub-group for the SO3. This is essentially generates the 3D rotation. Because that's a subgroup of the entire Lorentz group. Okay? We also emphasize that if you arrived here, now you can simply justify to yourself whatever representation you write down for this J and K generator. This commutation relation does not change. Okay? Okay? For the same group or for the same algebra. If you don't change the group or algebra, this commutation relation will not change. Then you really find something really intrinsically associated to this algebra, right? Meaning that you can change, you can switch to another representation. Okay? You can write down another matrix for this J1, J2, J3, J1, J2, J3. But this still satisfies such kind of relation. This relation will not change. Because this relation, as I said, intrinsically defines algebra itself. Okay? Yeah, maybe it's time to break. Let's have a break and then continue. again. 不要录屁股，就要听到。说的好。太激烈了。 So let's continue. So we introduced the SO1,3 algebra. Of course, that's not our goal, right? Our goal is try to introduce Spinor. Somehow. The first step is try to re-understand the Lorentz group or Lorentz algebra, Lie algebra of the Lorentz group in a slightly different way. Okay? Because as you can see, we said that the JJ can commute back to itself and JK is somehow mixed. Okay? But you can redefine a little bit. Redefine the generator. I can redefine the generator. Say I can redefine the J plus, define the half or the average of J and K, J and IK. Okay, I can redefine this way. I can have a J minus. They are redefined half Ji minus I. Okay. Okay. Now, of course, you can back to we can re-express J and the K in terms of plus and minus also, right? For example, let's use a shorthand notation. Let's say just use a vector. Vector is essentially the same as the I index, okay? Because I run from 1 to 3. I can use a shorthand notation. This essentially means the J plus J minus, you get back to original J. In order to get back to the original K, you have to use the J minus J plus and times an I, okay? Because we, after we do this redefinition, we shouldn't forget the original J and K. Why? Because there's a particular physical meaning of this kind of J and K. This kind of J and K generate physical rotation in the space. On the other hand, this is just a rewrite. So whenever you do your redefinition, you have to don't forget the original generator, which has a particular physical meaning. Okay. So so this means what? So if you can easily check yourself. By doing this redefinition, you get a new set of algebras for this J plus and J minus. Okay. So in terms of J plus and J minus, these commutation relations becomes more simple. As you can check. Right? As you can check, then you will get a simpler commutation relations. For instance, if you work out the commutator of J plus, you will essentially get back to J plus with an I epsilon. Okay? And if you calculate the J minus commutator about J minus, say, you will also get back to the J minus generator itself. Same J minus, okay? But with different index, of course. And you also find that this mixing between plus and minus are trivial. This gets simpler, right? Compared with this one, see, there's a little mixing in J and K. But now I redefine this object. I get a simpler commutation relations. Okay? This commutation relations essentially says that both J plus and J minus form a subalgebra. Okay? You see clearly, right? And they don't touch each other. Okay? There's no mixing. So mathematically, this essentially means that this SO1,3 algebra, it can be decomposed as 2 SU2. they summed together. Okay. Because as I said, we use this one to define SO1 conjugate. Now we also mentioned this kind of structure or this kind of structure for both J plus and J minus are nothing but what you're already familiar in your quantum mechanics course. This is the SU2 algebra relation. Okay. Now we have two, so we put a sum. The sum just means you have more generators, you have more relations, algebra relations, but they are just don't touch with the existing one. So we put a sum. Okay. So this sum is in the algebra level. It's a sum. Now, if you go to the group element, okay, to group element level, this sum essentially becomes a product, right? Because we know the generator has to be put on the exponential to form a group element, okay? It really does the transformation, physical transformation, okay? Now it's easy now. So we eventually arrived at this conclusion, which means that we can sufficiently take use of the knowledge, the quantum mechanical knowledge about this SU2 rotations to re-understand the Lorentz group. Okay, because these are the two just equal. Okay, the two are just equal. So we somehow translated the job in order to understand the two copies of SU2. So now what is that one? So what is the algebra? Okay, so what is we already know the algebraic relation, but then what is the representation? Okay. What is the representation? Right? You have some formal algebraic relation or commutation relation. As I said, the commutation relation itself does not depend on particular matrix representation, right? Right? That should be clear. But in order to compute something, it's better to have a representation, okay? Right? Rather than a completely abstract object, right? It's better to find a convenient representation to write down this SU2 algebra, right? That's what we already learned from quantum mechanics. In particular, in your QM course, we already learned a lot. For example, we already learned that each irreducible representation of SU2 is characterized by a half integer. Say J, okay? J, we use J, the half integer. That's a property for the SU2, right? And furthermore, the dimension of the vector space, which as introduced in the very beginning, there is a vector space. The vector space has some dimension, right? The representation of that group element is really the operator or matrix act on this vector space. Okay, these are two different things, but we can combine the together to give a claim. So for each such kind of representation, which is characterized by a half integer j, the dimension of that vector space is 2j plus 1. Okay, this is the property for SU2. Okay. Then with this knowledge, now it's clear to classify the Lorentz, the representation of the Lorentz group. Now It's straightforward, right? Because there's just 2 copies of SU2. There's 2 copies of SU2. Now, we can claim the irreducible representation of the Lorentz group. They are characterized by 2 half integers. Okay. Because we have 2, right? Let's say 2 half integers. One is m, another is n. Okay? Put them together. This m and n representation should have 2m plus 1 times 2m plus 1, the degrees of freedom. Or this is just the dimension of the vector space. Okay. You see? This conclusion purely comes from the representation. It's the irreducible representations of the Lorentz group. Okay? And you might, if you are a careful person, you might realize that this is not completely agree with the Wegener's result. The key point is Wegener's result not only touch this one, but also demand the unitarity, which is the key difference. But up to now, we disregard the unitarity. We just purely classify in a geometric way. Okay? So in some sense, Wegener's classification is more physical. But up to now, we are not doing purely mathematical or geometric analysis. Okay? Those are correct, by the way. Okay, it's just a different level. Okay. For instance, we can take some example. Let's say we know the tensor field. For instance, some n rank. A tensor field, for example, can have n index. Let's say t mu1 dot to mu(n), where n index with a high rank tensor. This tensor field, we know this can represent a Lorentz group, right? Right? If it's a Lorentz tensor, right? We define in this way. We define the tensor by following its transformation property. So tensor field can represent Lorentz group. But if we have a tensor field, now how to fit with that category we just mentioned. So in this case, we can associate this tensor field to a n divided by 2, n over 2, n over 2, comma, n over 2 representation. If we think that this pair are these 2 quantum numbers, okay? As you can check, okay? For instance, n equals to 1. N equals to 1, this becomes a mu, right? It's vector field, right? It's vector field. Now, following this category, n equals to 1, which is vector field, belongs to half-half representation. Okay? Okay? It's just a little fancy way to classify the representation of the Lorentz group. Because as justified, Lorentz group can be decomposed as 2 SU2. I just using the SU2 classification language. We can put 2 quantum numbers. Okay. Let's say n equals to 1, then this is half. This is also half. So the rank 1 vector, Lorentz vector, belongs to half-half representation. Okay. Is that clear? Now, as mentioned, we shouldn't up to here we should compare a little bit with Wegener, okay? Even though we know they are different, but you want to make everything consistent, you have to check back how to this representation classification of the representation here is consistent with Wegener. So as Conti has said, let's consider a mu field. According to the classification now, we know this belongs to the half-half representation. Okay. Now let's count in degrees of freedom. Let's count in degrees of freedom. For each SU2, we just claimed that for each SU2 there will be a 2j plus 1, right? For each SU2, there will be a 2j plus 1. So there is a 2 times half plus 1. Now there are 2. So it's square. This will equal 4. This is 4. However, we also know the from Wegener, let's see. Wegener, if you say following Wegener's classification for such kind of field, they actually are using a different quantum number to classify it, which is the m mass and the spin j, and the degrees of freedom has to be a 2j plus 1, say for a massive case, and it's always 2, something like that for m equals to 0. This is Wegener. There's no contradiction. Now we want to understand the relation, if there is. Okay, the result is different because we're going to demand the unitarity itself. That's the key difference. Which essentially means if you only care geometric classification to classify the representations in the rank 1 tensor, in this case, you after counting you get 4 degrees of freedom. Okay. Because you forget about unitarity, which means that you don't care the physical representation. Okay, you only care the geometrical representation. Okay, you still get 4. Okay, but Wegener tells you that there is physically demanding unitarity. For massive case, it is 2j plus 1. For massive, it's only 2. Now, of course, there is an important question here. Because there's both Wegener's classification and the classification here touch something related to spin, right? Right? In order to not confuse yourself, what is the relation between these two spins? Say, what do I see? Oh, yeah. So in Wegener's case, say for such kind of field, we said J should be equal to 1. So Wegener's classification, that spin, the definition of that spin in Wegener's classification, okay, is actually the spin of these two SU2 you add up them, okay? Because this is the half plus half equals to here 1. Okay? This is the relation. Because there are 2 copies, now we have 2 copies of SU2. Each has a spin quantum number. But if you talk about the Lorentz group, the spin for the physical spin for the Lorentz group, okay, that's such as Wegener's case, you should add up these 2 spin quantum numbers. This is the relation between these 2. But again, as I said, the classification is completely different. It's conditional. Okay. Now in both classifications, now we understand the vector, we understand the scalar, for instance, right? Scalar is also should be understood clearly, just 0, 0. Now the question is, now we have a new question came up. So all the discussions so far, if I follow this kind of category, say if I consider such kind of field, you add up these 2, you still get an integer. Okay. Now what if you have something a representation in this 2SU2 case? What if you have a representation something like this, okay, or this? Okay. You have a half for one SU2, but 0 for the other. Okay, it's allowed, right? Because nobody says these 2 quantum numbers have to be equal. No, right? It can be arbitrary. All the half integer is allowed, right? Because these are 2 half integers. Okay. So I can raise the question: what about this kind of representation? Is there any physical object corresponding to this kind of representation? That's the question. Now, in another word, as said, the physical spin is this add this one. So in this case, half add 0 is half. Okay. So what about the physical object carries the half integers, but the integers? The scalar has an integer. Vector here, the tensor. What about the half? So this is the question we want to answer. But before answering the question, we should do a little bit of analysis, right? As said, if you really want to go into the details of such kind of representation, first the question you should ask is what are the dimensions for the vector space? Okay, because this is trivial. This is half. Now you're counting the dimensions again. This should be the 2 times the half plus 1. This should be equal to 2, right? So we already know that whatever it is, the dimension of that vector space, this kind of representation act, the dimension is 2, okay? It has to be a 2-dimensional space, okay? The vector has to be 2-dimensional, whatever it is. That's for sure. And the other is trivial. The same thing for this one. We just exchange it a little bit. So the dimension is 2, and we also know that, as claimed somewhere, we also know that there is a typical one. There is a typical one to realize this SU2, okay? To just give a particular familiar representation, a convenient one, given by the Pauli matrix. Okay? Before you do any classification, you should first find some concrete representation in mind in order to do calculation. Okay? But very fortunately, we do have some metrics realize this let's say this a particular representation. Say for a single SU2, the quantum number is half. We do know explicitly one representation which is given by Pauli matrix. We can easily check, right? Do you still remember the explicit form of Pauli matrix? Yes? So you can easily check Pauli matrix from the SU2 algebra. Okay. Let's say I write that explicitly the Pauli matrix. Just you remember it's a sigma denotes the Pauli matrix. Okay. These are the 2x2 matrices. The 3. These are the 3 objects. So you see, since this is a 2x2 matrix, right? 2x2 matrix literally act on a 2-dimensional matrix. Okay, this is what we want. This is essentially what we want. So to be precisely, for half zero representation, we do have a realization of this generators. See, we just identify J minus as a half Pauli matrix sigma I, and J plus for this representation. I should expect J plus equals to trivial. Okay. Then you need to check such kind of realization. Given this sigma, everybody knows this realization. This representation indeed realized. This representation. Okay. This also means that the original physical rotation generator, which is J itself, is a half sigma, and the K, original physical K boost generator, is I over 2 sigma. Okay. And for the other representation, which is 0 half, we can do different choice. Let's say we identify J minus equals to 0, rather J plus equals to half sigma matrix. Okay, 2x2 matrix. Then you will get the relation with the original physical generator. Okay. So we call all the elements of the vector space act by such kind of group element generated by this generator. We call this as a spin half representation. We call such kind of representation spin half representation. Okay. As I mentioned in the beginning, as a physicist, we also call the vector space act by this kind of group element as the representation. So we just, without confusing, we just call those elements in that vector space as spin half representation. We call this also this essentially as a spin. Yeah. So we call the element of the vector space acted by spin half representation. This vector is nothing but spinors. Okay, you can take this as a definition of spinors. Okay, we define the object by how it transforms. Right? That's it. Okay, we define the object by how it transforms. That's just like Lorentz vector, right? We use the first two vectors. We define whether this object is the Lorentz vector or the Lorentz tensor. It depends on how it transforms. Here is the same thing. We first figure out what is the spin half, such kind of representation called spin half. And then we define the vector space. The element in that vector space acts on by such kind of representation. We call those objects as spinors. Okay. So because of the two dimensions, you can imagine this has to be two components. There has to be two components. There are two dimensions. Right? There are two dimensions objects. Okay. Now, because of everything now is we don't have any gap actually. We just try to follow them logically. We're just trying to identify or rewrite all the things which we have needed. In particular, we have such kind of identification. We already know the Lorentz transformation in a precise form in terms of J and K. It essentially means we can explicitly write down the Lorentz transformation matrix in terms of the new object. Okay. Okay. Which essentially means we already know how spinors, by definition. Okay. We already know how spinors transform under the transformation. Okay. Is that clear? That's right. Now I defined this object as the spinors. Okay, by this transformation. I also know the identification. Okay, we have this sigma and this J. And I know explicitly Lorentz transformation in terms of J and K, which means I know explicitly Lorentz transformation in terms of sigma. And the sigma is not about act on this spinors. So this means that I can really write down how the spinor transforms. Okay? For example, now, without confusing, now I just call there is a zero, this kind of representation, we record the label that they will come out half spinors. Okay? We call such kind of spinors the right-handed wire spinors. And we give a notation with the sign R. R means right. Okay. Following this identification, we can easily write transform. So the psi R on the Lorentz transformation, the psi R is transformed this way. Okay? As I said, this is nothing but original Lorentz transformation matrix in terms of J. I just rewrite it in terms of C. Okay? You see? We also know, this means we also know how the half zero spinors, which we call the left and wire spinors. We also know the transformation rules for this left. Okay? The difference is this is plus, this is minus. Okay? The difference comes from the original difference from the J and K, okay? Or the difference from this identification. This identification, there's a difference, sign difference. Okay? Now again, I keep asking you a question. Are these representations unitary or not? Can you observe something? Sigma metric is Pauli matrix. Pauli matrix are Hermitian, right? Okay. You see, because you take a conjugate, go back to self. Hermitian conjugate. You see? Okay. Then you can easily check such kind of transformation matrix cannot be unitary. Right? It cannot be unitary. Again, it justified that even though we came up with spinors now, some kind of new representation. Again, it seems it's not easy to find the unitary representations by finite dimensional space, you see, or finite dimensional representation. Okay? So it's not unitary again. This is the reason, or this motivates us, we have to go to field. Okay? Not only such a simple vector or spinors, okay? We have to go to field. So as before, we have to embed. Now we know such kind of object represents some half integer spin, right? This is a half integer spin object or particles, if you want. Now we want to really embed. Now we want to try to construct the field theory, try to incorporate such a half integer object. Okay. So we want to construct the arrangement for spinors. We also know what is spinors. But up to now, you have to be very clear. Up to now, we haven't touched the field, the spinor field, okay? From a field, okay? Up to now, we only talk about some very, very simple object in some vector space, okay? Okay. So what should we? Which kind of Lagrangian we should construct? That's the key question, right? Whether you can come up a sensible theory by promoting such kind of spinor into a spinor field. Okay? It's like the vector field, right? It's like the vector field, but it's the property is the physical property is different, but what I'm trying to say is now the logic goes as follows. We first understand what is spinor. Now you promote it to a spinor field, which means the field is the spinor valued. Okay, it's like a vector field. Right? It's like a vector field. So that means you can simply promote it to a field. We know the field. We know the field has to be a two component, it's two dimensional. So you might want to write it in terms of this way. Okay, we want to construct some sensible theory based on this field. Now go back to the last week's construction. You always should find the theory satisfying the symmetry, right? The first symmetry constraint is the Lorentz invariance, right? We should always find a Lorentz invariant theory. So the first task is to try to check which kind of combination or which kind of object or which kind of function object built upon that kind of object can be Lorentz invariant. That's the first question. Okay. Because we know all every detail about the Lorentz transformation. We can easily check ourselves, right? Like that. Now you might complain that okay, this is exponential, this is the matrix. It always bother me how to calculate it in practice. You know, this is complicated. That's fine, but there's a trick. You see, if you're bothered by this, then what I can tell you is that there's an infinitesimal version, right? Which is the expansion. The center these parameters are small, again, you can do the expansion. You can do the expansion because this will be equals to 1 plus this one. This is the first term. You see, 1 plus. This is the first term. Now from here, you can immediately read off what is the infinitesimal change of the R, right? Just subtract delta. So delta will be equal to half I theta j plus theta j sigma I. Similarly, there is a delta for cosine L, which is half I theta j minus theta j sigma j cosine L. Okay. So you know the simplified, which is infinitesimal version of the Lorentz transformation of these spinors. You see, right? This provides you a convenient way to justify which kind of combination can be Lorentz invariant. For example, you might just check. Okay, just check. You probably we don't know, so let's do experiment. Okay, you check. You might want to check such kind of combination. I can choose, since this object looks like this way, I can choose to consider the cosine R dagger. Okay, dagger is defined in Euler case. So this is transform. Take a conjugate. Is that clear? Yes. So the answer is no. Unfortunately, this is not a Lorentz invariant. Okay. You can also check that some combination looks like this. Dagger. Separately, either this or this, they both are not Lorentz invariant. Because this you didn't get zero, right? There's a if you follow in such a rule, just calculate this one. But very fortunately, if you combine them together, you'll find the delta of this part is actually equals to theta I. This one. And the delta of this one is actually equals to beta I minus theta I epsilon ijk. Okay, you find this one. This looks familiar. This means what? This means if you take this entirely as a zero component of some new object, and this with an I index occupies the three component of a new object, which means you take it as a whole. This as a whole as a four vector. Indeed, they transform as a Lorentz vector. That's very lucky property of such kind of combination. Okay, because you can check this is nothing but the property. If you the delta of the zero component, you get the beta I. Okay, your beta I times the later part, and the delta of this the later part, you get the beta I times the zero component and the minus theta I epsilon ijk times this part. This is precisely the infinitesimal transformation of a Lorentz vector we write down in the beginning for xi. Okay, this is the property for xi, transformation for xi. So this means that you shouldn't consider them individually or separately. Rather, you should take them as a whole, right? With a common, these are three objects here. I round from 1 to 3. This entire thing is a Lorentz vector. Okay, this you can easily justify. Okay? It's not much calculation. It's easily checked. This motivated us. Okay, since if this is true, then I can try to construct the Lorentz invariant compilation. Looks like this way. The experience, the lesson is that in order to construct some vector, you have to insert some sigma matrix. Okay, sigma matrix here. So we can use a psi dagger sigma mu, let's say partial mu psi r. We can use such kind of combination to construct Lorentz invariant objects. And you can check it. This is indeed is a Lorentz invariant, provided this sigma mu is defined as the first component is 1, and the later three component is nothing but sigma 1, sigma 2, and sigma 3. Okay, is it clear? This is the structure is a little complicated, but it's not. It's okay, right? This mu is an index, the run from 0 to 3. Okay, but for each mu, there are also 2 by 2 matrix. Okay, you see? So for each mu, there are also 2 by 2 matrix. That 2 by 2 matrix act on the two component object, which is the spinor. Okay, this derivative is just usual derivative, right? Right. Then you can check. This is indeed a good Lorentz invariant candidate. So because of this, we can actually write down the final answer. The final answer, let's say, similarly, we can also justify the some kind of mass term. Let's say only you combine with right together with left, you can get Lorentz invariant. Because we already said by itself, right combined with right is not. Okay, the right combined with left, so you get a Lorentz invariant. So such kind of term can be viewed as mass term. So indeed, you can eventually write down the Lagrangian have nice property. Include both left and right. and also with mass terms. These are good Lagrange for the spinors. By now, it's only two component spinors, but include both left and right, right? Now you just rewrite a little bit, you realize that this is nothing but the Dirac Lagrange. Okay? Because there are two copies of, it's not two copies, but there are two pieces of two components. You can repackage a little bit, forming the four component spinor, okay? And with a 4x4 matrix, you just rewrite the same Lagrange a little bit. You can realize that this is nothing but Dirac. The Dirac Lagrange. Okay? You can rewrite four component spinor and write the sigma, package the sigma, all this sigma 2x2 matrix into a bigger 4x4 gamma matrix. Okay? And yeah, just redefine your spinor. Let's say I just redefine my two component spinor. I put them together. A two component. So this has a four component, and I define the precise bar. Also in this way, I get a four component. A spinor, you can check that up to this kind of rewriting, this Lagrange is nothing but the familiar Dirac Lagrange for four component spinors. Okay. And from here, you can also derive the Dirac equation, things like that. It's pretty elegant. Okay, so we should end today's course. The last few words is that in history, Dirac theory, Dirac Lagrange was not a discovery in this way, for sure. Okay, it was discovered in a completely different way. It's actually for a wrong motivation, for wrong motivation. Yeah, that's true. Because Dirac theory was initially discovered to solve the relativistic quantum mechanics. But we already argued in the first lecture that relativistic quantum mechanics doesn't make sense. We have a lot of issues. But the Dirac, the precise mathematical form of such kind of Dirac Lagrange was invented at that time for that purpose. But that purpose was wrong. Okay? But eventually, people realized that, okay, the Dirac, the four spinor object, should be understood as a spinor field. That's the correct interpretation. Rather than some wave function for some time. But we already argued in the first lecture. That's the wrong way. There's also another way to understand the Dirac theory, in particular this fancy object. Because if you do such kind of object twice, you'll get a precisely Klein-Gordon equation. So this is the reason sometimes people say just, okay, let's take a square root of Klein-Gordon equation and get a Dirac equation. That's not very precise, but indeed, you can check the relation between them. If you just view this whole as an operator, and you act twice, you will get a precisely Klein-Gordon equation. Okay, you can check it in the equation motion level, right? Yeah, we will continue next time. We will explore a lot of different features of this Dirac equation, including quantization or all the properties, charge conjugation, or different spinors, wire spinors, Majorana spinors, whatever, different representations. We're going to do it next time. We stop here.